To this morning's session on nano and emerging photovoltaics. We have three presentations scheduled for this morning. We'll start off with Professor Matt Law from UC Irvine, who will talk about quantum dot solids for photovoltaics.
Okay, thank you. Good morning, everybody. Welcome back. So I'm going to pick up where I left off yesterday. So yesterday we had talked about quantum dot synthesis. Oh, yeah, the mic again. Quantum dot synthesis, and we talked about the fabrication of quantum dot thin films. And a little bit about charge transport and kind of ideal quantum dot superlattices, where we said we could get mini-band transport. Today we're going to talk about transport in real arrays of nanocrystals of various kinds, and get into some of the solar cell parts of the discussion. So this is where we finished last time. We talked about these ideal superlattices of quantum dots, where we have everything perfect in terms of no disorder in terms of size or spacing, etc. And we have an energy landscape for electrons and for holes that look like something like that. But the ideal case, or the real case, is somewhat different. So in the real case, we have an array that might look like this. It's actually not an array at all. An assembly of quantum dots in which we have a distribution of quantum dot sizes, shapes, the distances between the dots are all different, and we have an energy landscape that might look something like this for the first these three middle quantum dots there, where we can see we have band gaps that differ depending on the size. So the smallest quantum dot has the largest band gap. We have barrier widths that are different depending on this separation being larger than that separation. We also have the presence in here of states within the band gap, which is something that we hadn't thought about before. So if we have traps within the band gap, that's also going to increase the disorder within the array, and that's going to change the charge transport properties. So the fact that we have a complete lack of periodicity, that we have variations in interdot distance, that's going to change the coupling between the quantum dots. Variations in the quantum dot size and shape will change what's called the site energy, which is basically the homo-lumo energy of the individual quantum dots. And surface states of the band gap are all going to be important in determining the actual properties of these arrays. And so we can kind of think about charge transport in real quantum dot arrays using about 3 or 4 different parameters to try to kind of conceptualize what's going on. So the first important parameter is the exchange coupling energy, which we use beta to describe that. This is basically the quantum mechanical exchange coupling that happens between quantum dots when you move them together and the wave functions overlap. You get a splitting of the energy levels, and you get energy levels that become bonding-like states, like in molecular orbital theory, and anti-bonding states. And depending on the distance between the quantum dots, where L here is the edge-to-edge distance, as we make that parameter smaller and smaller, we expect to get a larger and larger splitting between these energy levels. And beta, the coupling energy, is going to be proportional then to the overall bandwidth or spacing width between these levels. The coupling energy we can actually describe in terms of a very simple expression. So beta, the energy, is equal to Planck's constant multiplied by gamma, where gamma is the tunneling rate between two dots. We can express gamma as is here. So gamma is equal to some sort of attempt frequency, gamma 0, multiplied by a distance-dependent exponential and an energy-dependent exponential. And this distance-dependent exponential has properties of the insulating barrier. So we have the effective mass in the barrier, we have the barrier height, which is EB, and we have the barrier width, which is L. So that's the edge-to-edge distance of the quantum dots. So this tells you basically that you have an exponential decay of the wave function within the barrier, which is what we would expect. We also have an energy-dependent exponential, and this is for tunneling from one dot I to another dot J. We're going to have the difference in energy between dot J and dot I as being the important activation energy for this process. So we can think about this as phonon-assisted tunneling. For an entire array, we can condense this component of the expression to kappa, which is basically the decay parameter for the wave function. And so we have this for this expression for an array of quantum dots. We can use beta and use gamma and the expression that Einstein came up with to couple the mobility to basically the diffusional parameters of a material, to understand what sorts of betas we would expect to get kind of different types of mobilities. So this little chart down here shows, like for example, if we wanted to get a mobility of 5 using this kind of hopping transport, That corresponds to a residence time within a quantum dot of about 500 femtoseconds. And that corresponds to, in turn, about 8 MeV coupling energy. So not very large. So we can get a very large mobility. That's quite a large mobility. It's not as large as what we can already get with quantum dot solids, but it's close. It's within a factor of 5. We get that with a pretty small beta. More common mobilities for quantum dot solids are like around 0.01, 0.05 here is shown. That has a beta of about 80 micro eV. So very, very small coupling energy gives you a pretty large mobility. So that's the first parameter that's important. A second parameter that's important is the so-called charging energy of a quantum dot in film. So charging energy takes into consideration that we have electron-electron repulsions in the films. And it's the charging energy is defined as the energy it takes to add an electron to a neutral quantum dot. And that energy for an isolated quantum dot looks like this. So the energy is E squared over 2 times the capacitance. And if you do the capacitance, self-capacitance for a sphere, you get an expression that looks like this. And that comes out, depending on what R is, between 100 and 300 MeV. For an isolated dot, that's the charging energy. So that's substantially larger than KT. That could be a problem if we were talking about just trying to flow charge through isolated dots. For dots and films, however, the charging energy is a little bit different. It's a little lower, and that's because we have extra capacitive contributions between the nearest neighbor particles that are surrounding an individual quantum dot in film. And so we expect to have a charging energy that's not just the self-capacitance of the single dot, but it also has a contribution from n nearest neighbors. And each of them in this particular expression is considered to be an equal contributor. If you have this sort of quantum dot in a film, that lowers the charging energy substantially, and depending on exactly what the numbers are that you're using, you have between, say, 1 and 15 MeV. So now we're less than KT. So basically, in a film of quantum dots that's highly coupled, especially for lead selenide or lead telluride or one of the lead salts where we have a large dielectric constant, we can have charging energies that are pretty low. And at room temperature, it turns out the charging energy is really not that important in terms of governing the charge transport properties. However, there are cases in which the charging energy, if the charging energy is larger than the coupling and larger than KT, and so that might happen at low temperature, and that might happen when beta, when the coupling is weak, then we have a charge transport bottleneck, and this is something called the Coulomb blockade, and this is going to inhibit charge transport, and you're going to have what's called a Mott insulator. So a Mott insulator is one in which electron-electron repulsions are basically localizing the electrons within the array and preventing rapid charge transport. So Mott insulator is one potential problem, but as I say here, this energy is fairly low, and so we don't consider this to be a major problem for at least lead selenide at room temperature, as long as it's strongly coupled. The third parameter that's important is the so-called site energy disorder, which was given the term delta alpha. So the site energy disorder is fairly easy to understand. If you have any real quantum dot array, you're going to have a distribution of sizes for the quantum dots in that film. And that, because of the quantum quantum size effect, means that our HOMO and LUMO levels are going to vary throughout the film. So the physically small quantum dots will have a large band gap, and the physically large quantum dots will have a small band gap. And that leads to kind of a corrugated energy surface for electrons and for hole transport. And this distribution we call delta alpha. Now delta alpha for a good array, a good size distribution quantum dot film, you might have about 5% polydispersity. And that then, we can estimate what the delta alpha parameter is going to be with about 5% polydispersity, so that we have a delta R of about 5%. That gives us about 50 to 100 MeV in terms of the site energy disorder. So this is larger than KT. It's actually quite a bit larger than typical coupling energies too. We can experimentally estimate what this parameter is, this delta alpha, by looking at the first exciton energies and fitting these and looking at the broadening of the peaks. So full width at half max for these different first excitons for lead selenide come within this range of 50 to 100 or so MeV. Now again, if the coupling energy is much higher than delta alpha, then we don't have an impediment to charge transport. But if we have the opposite situation, if the disorder is larger than the coupling and larger than KT, then we can have the disorder localizing the electrons and giving us what's called an Anderson insulator. So an Anderson insulator is one in which disorder causes localization of the electrons and inhibits charge transport. So those are three parameters. There's a fourth that's not really included in some of the normal discussions. And the fourth basically is kind of an aggregate of other forms of disorder within the film. So we have variation in coupling energy because of differences in interdot distances, differences in area of interaction between quantum dots, which can lead to differences in coupling, and in orientation. We also, as I mentioned, have a lack of long-range periodicity in the film, and so both of these factors are going to disrupt or make it more difficult to form extended states. But perhaps the most nefarious form of disorder that's not included in the typical discussions are surface states in the band gap, so gap states in general. If we have gap states, then basically it effectively increases the delta alpha by a lot. Okay, so what I show here is a density of states picture for quantum dot, let's say film. Here's the 1SH, so this is the HOMO. Here's the LUMO, the 1SE. And we just put the Fermi level somewhere in the gap. It doesn't really matter. There are basically two different kinds of band gap states that we need to be concerned about. The first are the so-called band tail states. These are states that tail off into the band gap. They might extend by 100 MeV or so into the band gap. These are caused by things like differences in coordination and differences in bond length and orientation. The second kind of gap state are the so-called deep gap states. And these can be in various locations within the band gap. And these are typically created by things like dangling bonds or impurities or adsorbed molecules on the surface, things like this. And usually they're modeled as Gaussians or something approximating the Gaussian. If these states are present in the gap, and they almost always are, we think, in most quantum dot solids, they are by far the largest and most damaging source of disorder within these films. And they will trap carriers, they'll cause recombination, and they can lower the mobility by orders of magnitude. So we can sum it all together here in a kind of basic picture by putting together an electronic phase diagram for these kinds of disordered films. And this is a diagram from Remical and Levine, 2001, showing the different kinds of behavior that we would expect, very localized or delocalized kinds of wave functions, as a function of the disorder along the y-axis and the coupling energy versus the coupling energy versus the charging energy along the x-axis here. And so we have two different ways that we can make very localized insulators. We can make Mott insulators here. Mott insulators would be when the coupling energy is very small compared to the charging energy. We would be in this region. We can make Anderson insulators. That's when the disorder is very large. And so the picture that we would expect to see there for those two particular situations is we would have an array of nanocrystals like this with the wave function localized on a single nanocrystal. And it then would hop or tunnel with phonon assistance between nanocrystals as its method of motion. Alternatively, we can have a kind of intermediate amount of disorder and an intermediate amount or intermediate charging energy. We can have domain localization, where the wave function extends over a pool of quantum dots in the film. Maybe a few, maybe 10, who knows exactly what, depends on the conditions. And then, of course, at the other end of the scale, if we have strong coupling and we have low disorder, we can have a delocalized situation, where the wave function extends in principle over the entire quantum dot array, like it would in an atomic solid. So that's the basic picture. So experimentally, what do we see? So experimentally, what we have is, we can consider what the condition is for actually achieving band-like or mini-band transport. The condition basically is that the coupling energy has to be larger than everything else. Coupling energy should be larger than the site energy disorder, than the charging energy, and then KT. The actual situation for almost all, or probably all quantum dot films made so far, is this. The disorder is larger than KT typically, which is larger than the coupling, and the coupling is maybe a little bit larger than the charging energy. And so what have people actually seen in experiments, and experiments that are designed to actually look to understand what kinds of charge conduction mechanisms are at play in these films? One way to look at these questions is to take conductivity versus temperature plots. And this is data here from the Frisbee group in Minnesota. What they were looking at is lead selenide dots, and they found basically that you have two different regimes of charge transport. At high temperature, they have kind of normal Arrhenius behavior. So we have high temperature up here. Arrhenius behavior is given where the conductivity is proportional to e to the minus t to the minus 1 power. So the normal kind of activation energy that you would expect. When you see that sort of behavior, t to the minus 1, This is consistent with what's called nearest neighbor hopping, and I'll describe what that is in a minute. But they see a change in the slope of their Arrhenius plots when they go to low temperature. Okay? At low temperature, the slope changes from 1 to 0.5. So here, this is low temperature, this is low temperature here. So this graph shows a nice way to actually get the slopes out. They're 0.5 at low temperature and about 1 at high temperature. At low temperature, when you have a t to the minus 1/2 dependence, this is characteristic of a certain type of variable range hopping transport. It's called ES, variable range hopping. And so what are we talking about here with these hopping mechanisms, right? It's very different than band-like conduction, very different than mini-band conduction. Nearest neighbor hopping happens at higher temperatures, I said, and this is basically what it sounds like. You hop from this quantum dot to its nearest neighbor and so forth, sequentially and incoherently. And this is the kind of expression that you can use to describe nearest neighbor hopping. You have, t to the minus 1 power dependence. Variable range hopping kicks in at lower temperatures. So at lower temperatures, it turns out that the carriers may not have enough energy to go over the activation barrier, essentially to hop to the nearest neighbor. And it may be more probable for a carrier to instead tunnel to a distant quantum dot within the film that has a more resonant energy. So even though it's farther away and you pay the distance penalty, it's still preferred over hopping up to a higher energy state. This is at lower temperature. And so this is called variable range hopping. And basically, instead of the hopping distance being d, where d is the center-to-center distance of the quantum dot, the hopping distance becomes x prime, or x star, where x star is basically a function of temperature. And this is the expression for x star. X star is chosen so as to maximize the conductivity within the film. And you can see that as the temperature goes down, x star increases. That means that the average hopping distance increases as the temperature falls. This is because the electron or the hole is searching out more isoenergetic states that are farther away from itself, in preference to actually try to overcome an activation energy that it can't because of the low thermal energy in the film. So this is typically what people think is going on in these quantum dot films. We have nearest neighbor hopping at higher temperatures. We have variable range hopping at lower temperatures. So now let's get into solar cells a little bit and see how this applies to some of the solar cell physics that we care about in improving these devices. This is a nice montage from Randy Ellingson of the progression of quantum dot solar cells over the last 10 years, from the descriptions of multiple exciton generation through sort of the first quantum dot films that were made into solar cells in about 2007, 2008, and then the progression in terms of understanding and the efficiency of devices. So certified efficiencies of 2.9, then 4.4, then about 5.1. And today, the Sargent group in particular is producing devices between 6 and 7%, maybe a little bit higher than that. Yeah?
I have a question on your last slide before we move on to your asking now. So you talked about at low temperature, you think the conduction is through a variable range hopping mechanism, which can occur on very long distances like that. So would that indicate that if you had perfectly monodispersed lead selenide quantum dots and you left OVA on, at low temperature you have good conduction, because then the dots would not be anywhere near as far as what you have drawn there, but your energy states would be very degenerate.
So what this is telling you is that you go into the variable range hopping regime, but your conductivity is still very, very low because you've got this long hopping distance that you need to accommodate. So if you had quantum dots that were insulating at room temperature because they had the oleate ligand present, I don't really know what to expect if you go to low temperature. I think that you might eventually have around the same conductivity for both cases. So if you had a perfectly monodispersed film, but they were well separated, versus polydispersed film, but they were tightly coupled. I think at some temperature you're going to reach a conductivity that's very low in both cases, but nearly the same. That's my intuition, but not really sure. Okay, so this just gives you kind of an idea about the progression of the field over the last 10 years or so. The initial devices started out as Schottky solar cells. So if you remember, a Schottky solar cell is one in which we have a junction between a semiconductor and a metal. And in this case, this was work from my postdoc with Joey Luther. So we have a back contact Schottky solar cell where we have lead selenide film here and a metal here. This is where the back contact field is present. This is what the band diagram looks like. And these devices produced pretty good currents, so over 20 milliamps, pretty small voltages, so overall efficiency was about 2% or so. And this is the external quantum efficiency, and what I really want to point out is the EQE. It's pretty high and visible, it tails off substantially into the IR. So we moved from Schottky Devices, which had the junction at the back contact, which is not very optimal for a high-efficiency device. The innovation over the last few years has been to move to a window layer PN heterojunction type of geometry, in which we have a structure where we have a transparent conducting oxide of some sort, then we have a window layer that's usually zinc oxide or titanium, and then the quantum dot film, and then a back contact. This kind of geometry is advantageous because it puts the electric field right at the interface at the front of the quantum dot film, and so we can more easily collect the high energy carriers. And also, because it's PN junction, it tends to have better voltages than the Schottky devices do. And so this is what a band diagram for this would look like, a typical one. This is some work from the Sargent group showing a 5% device. And again, the EQE, strong and visible, so this is 80%, and it tails off pretty substantially into the IR. One of the best EQEs of any of the devices I've seen yet is from work at NREL. This is work by Tavi Simonin at NREL. Showing a device, in this case ITO zinc oxide lead selenide gold, that produces about 32 milliamps per centimeter squared, which is a quite nice short circuit current. Again, the thing I want to point out is that we're losing a lot of current in the infrared part of the spectrum, right, in the near IR. And the reason this is the case in all three of these devices that I've shown is because the diffusion length for, in this case, electrons, sometimes for holes, is too small in the film. And so this forces us to use very thin layers of quantum dots, something around the order of 200 nanometers or 300 nanometers, or in this case a little bit thicker than that. And because we use optically thin films, we're going to lose red light absorption and collection. And so I'm wondering if there's a way that we can increase the diffusion length so that we can actually thicken the films and collect lots more red carriers. So, as a little bit of background, just to make sure everybody's on the same page, I've been talking about mobility for a while. So mobility mu, that's a proportionality constant between the electric field and the drift velocity. So basically, the higher the mobility, the faster carriers will move. And of course, I raised this before too. This is the diffusion length, LD. It's mu times tau, which is the lifetime of the carrier multiplied by the thermal voltage. The diffusion length is a critical parameter in solar cells because it gives the characteristic distance that a carrier will move before it recombines. And so in order to get large photocurrents from devices, we have to have diffusion lengths for minority carriers that are thicker, that are longer than especially the quasi-neutral region in the film. And the quasi-neutral region in this case, I'm talking about this portion of the quantum dot film that's not in the electric field. And this quasi-neutral region also has to be thick enough to make sure that all the light is pretty much absorbed. So we need a film that's somewhere on the order of a micron, a little bit thicker than that. And so we need diffusion lengths that are sort of on the order of the micron too. Currently, what we think is going on with diffusion lengths in quantum dot films is that we're at about 50 nanometers or so. And this can come about by having 10 nanosecond lifetime, carrier lifetime, and a mobility of 0.1 centimeters squared per voltsecond, which is fairly typical for organic ligand exchange films. So what we want to do is to try to increase the diffusion length. Let's first understand exactly how thick of a film we're going to need to absorb all the sunlight. So this is data here, the optical absorption length versus energy for several different samples of lead selenide and lead sulfide quantum dots. And what this is telling us is basically the optical absorption length at each of these energies. So 100 nanometer optical absorption length at about 2 eV, going up to about 1,000 nanometers or 1 micron at about 1 eV, right? Close to the first exon transition. The first exon transitions are these inverted peaks here. So in order to have full, nearly full light absorption from these films, we want to be at about 3 absorption lengths thick. And if you include the back reflection, the double pass, we basically want to shoot for a diffusion length in our films of about 1 micron. That's a nice number to target. That would allow us to at least collect a lot of the photons, or almost all of the photons in the solar spectrum, from the absorption coefficient, or from the absorption threshold onward. So if we want to target 1 micron diffusion length, what do we need to do to be able to achieve that in terms of getting mobilities and lifetimes? This is a plot here showing mobility, or sort of showing diffusion length here as a function of mobility at various carrier lifetimes, from 10 picoseconds all the way up to a microsecond. This dotted line here is the 1 micron diffusion length that we're targeting. And if we look at the mobilities that are experimentally accessible to us right now or in the near future, that's this blue bar here, this band. These are kind of the mobilities that we can expect to achieve from quantum dot solids. And so that means that the region of interest for us is kind of up here in this orange rectangle. And what we want to do is then achieve some minimum carrier lifetime and some minimum mobility so that we can get up to about 1 micron diffusion length. For example, if we had a lifetime of 10 nanoseconds and a mobility of 40 centimeters squared per volt second, then we would have achieved our goal. Okay? As long as we can do that for the minority carrier, of course. The lifetime of 10 nanoseconds is pretty standard in some of our film preparations, and the mobility of 40, as I'll show you, has already been achieved for certain quantum dot films. Okay, so in order to study mobility, or to study diffusion lengths, what people are often doing is studying mobilities. And to do this, the most common platform for studying mobilities is the field effect transistor, or the FET. And so we do a lot of FET measurements in the field, and I want to cover just a little bit of this before concluding. So a field effect transistor is basically a 3-terminal electronic device in which we use a gate field, so voltage supplied to a gate electrode, to modulate the current that's flowing in a channel of nanocrystals between a drain contact and a source contact. And so by changing this gate voltage, we can change the amount of current that's flowing. We can also use this platform here to determine what the mobility is, the field effect mobility. The field effect mobility is going to be proportional to the slope of the current divided by the voltage, the gate voltage in this case. And so a lot of people study quantum dot FETs, and we've done so too. So here's an example of a quantum dot FET study in which we looked at the effect of ligand length on mobility. And what we decided to do is take a certain sample of lead selenide dots, 6 nanometers, and to take a number of alkane dithiols with different alkane chain lengths, from 2 carbons, so we had ethane dithiol, all the way up to 6 carbons, or hexane dithiol. This is kind of the output characteristics that you would see for an EDT-treated field effect transistor. These are ambipolar transistors, meaning that you can conduct holes or you can conduct electrons, depending on what the gate field is. And this here shows a current versus VG plot. So these are called transfer characteristics for representative devices having these different molecules on them, EDT all the way down to HDT, hexane dithiol. What we see is that the mobility is proportional to the slope of this plot. And so the slopes here progressively get smaller and smaller as we increase the length of the ligand between the nanocrystals, between the quantum dots. And so what this is telling us is that the mobility is highest for the shortest interdot spacing and it's lowest for the largest interdot spacing. And we can take the mobilities that we calculate and we can plot them on a semi-log plot versus the nominal length of the ligands, these different alkane dithios. And what we get is a nice line for both electron transport and for hole transport. This is telling us that we indeed have an exponential dependence on the mobility versus the distance between the quantum dots. Exactly what we would expect for tunneling kinds of transport. And we can understand the mobility as, again, a product of an exponential distance and energy term. We can go through and make sure that everything makes sense. These kappa values here, which are the decay parameters for the wave function, turn out to be around the value, 1.1 or so inverse angstroms, that you would expect for tunneling through alkane types of barriers. And so this kind of study confirms charge transport by tunneling. We've gone on to spend a lot of time trying to understand mobility as a function of various important parameters in the film, not just ligand length, but also the quantum dot size and the size distribution. I don't have any time to talk about the results, but basically what I want to point out here is that if you notice what the maximum mobility is for each of these cases, it's about 0.1 or so for electrons. For organic molecules, organic ligands, typically 10 to the minus 4 to about 1 centimeter squared per volt second. That is the range of mobilities that are pretty accessible. What I want to do finally here is discuss some ways in which the field, not just my group but others in the field, are trying to go beyond this 1 centimeter squared per volt second to try to achieve very high carrier mobilities in films. I'll show 3 different examples. The first example is from the Talipin group at the University of Chicago, where they're using, and each of these 3 examples is going to be the use of an inorganic ligand instead of an organic ligand to do the coupling of the dots. In their case, what they've developed is metal chalcogenide complexes that they can use as ligands They take an organic capped dot and they exchange with one of these MCCs, these metal chalcogenide complexes. For example, tin 2S6 4- is one particular MCC that they use. This completely exchanges the organic, gets rid of it, and you have an inorganic charge-stabilized particle. And this is an example of a bunch of these particles in solution, in this case, fairly polar solutions, charge-stabilized. So you can make nice inks from these and then make films. So what this group particularly has done is use field effect transistors to study mobility. And so what they did is their fabrication, they took spin coating from cadmium selenide quantum dots that were coated in these MCC ligands. They make a film that way, then they anneal this film at about 200 degrees C for 30 minutes or something like this. And the annealing process has a couple of different functions. First of all, volatilizes any residual liquid that's present in the film, but it also converts this MCC, in this case they were using an indium analog, into an inorganic semiconductor, basically. In this case, indium-2, selenium-3. The other thing that the heating does is it seems to cause necking between the quantum dots. And you can see a little bit of that by looking at the optical absorption spectrum. Before is in the red, and then after the heat treatment is blue. You can see that the broadening of the first exciton transition and the redshifting of the first exciton transition, as I said before, that indicates some coupling, dielectric changes, and also probably an increase in the size distribution. And so this is probably good evidence for an increase in delta alpha. The other thing that they do is, in any field effect transistor, they use the gate field to fill traps within the material. And by doing that, they are able to get electron mobilities of about 15 for these kinds of films. If they push the heating parameters to a little bit higher temperature, they can get to 30 plus in terms of electron mobility. And this is far and away better than what's been achieved in the past. It's better than amorphous silicon for sure, and most organics, if not all organics that aren't single crystals. So that's one avenue that's being explored. The second is from the Murray and Kagan groups at Penn State. They're using inorganic ligands as well, but they're choosing to use thiocyanate instead, and they're going to combine thiocyanate and doping with indium to achieve high carrier mobilities. So they can do the ligand exchange into thiocyanate. They spin coat, again, these are cadmium selenide quantum dot films that they're making. They do a 250 degrees C anneal in this case. And a number of things, again, are being achieved by this anneal. They first volatilize or dissociate the thiocyanate molecule and form basically a cadmium sulfide surface on each of the quantum dots. Definitely we're getting necking between the quantum dots in this particular case. And one of the most important things is that by heating up the film, they're reducing diffusion of indium into the film, and indium is acting as a dopant to basically fill traps and increase the Fermi levels. So you can see here optical absorption spectra of the film before heating here in red, and then after heating in blue. So you can see that the first exciton transition is almost completely washed away. That's a great indication of a lot of delta alpha increase. This plot here shows the effect of having indium present nearby. They use indium as electrodes, and the conductivity here versus the annealing temperature. Without indium, with just aluminum electrodes, the conductivity stays very low, but with indium electrodes, the conductivity goes up very substantially. And they think that what's happening here is that indium diffusion is causing the Fermi level to rise because of donor-like dopants, and that's filling a lot of the deep traps within the film. That's allowing the mobility to then be higher because these deep traps are already filled. And plus, they use the gate field to further fill traps within the material. And they're able to achieve electron mobilities of about 25 or so. So we're, the field of cadmium selenide quantum dot films is around 30-ish, 25, 30, as the record mobilities at the current time. And those will continue to rise. Do I have a few more minutes?
Yeah.
Okay. So the third way that I want to discuss about how people are trying to improve the mobilities and hopefully the diffusion lengths of these films is work from our group, where we again are taking an inorganic ligand, in this case sulfide, and we're combining sulfide capping with infilling of the interstitial spaces between the quantum dots by using atomic layer deposition. So basically we're trying to change the matrix material from air to some other more functional material. So what we do in our case is we do a dip coating process to make a sulfide capped film. So each of these little blue dots is supposed to represent an S2 minus. S2 minus, of course, very small, and so the particles are brought very close together. And then what we do is we use low temperature atomic layer deposition to infill all the spaces between the quantum dots. And what we think happens as a result of this is that we combine the strong coupling from the sulfide treatment with surface passivation of surface states from the, in this case, Al2O3 or amorphous alumina that we deposit into the film. And what we're able to achieve then for reasonable temperatures of ALD infilling, say about 75 degrees C, we can get electron mobilities of 8 or so centimeters squared per volt second, which is the highest yet for lead chalcogenide compounds. The other thing that's interesting, an interesting result of the ALD infilling process is that we generate a very environmentally robust material. So this ALD layer acts as a very good vapor diffusion barrier. And so we can bring our materials out into air, and for months we can store them in air, and the mobility for this particular film doesn't change. The mobility for this one maybe changes a little bit in the direction that we would actually like to see. Right? So a very small increase in mobility. So these are air stable and high mobility lead-X quantum dot FETs. So this is just a description of what atomic layer deposition is, in case you don't know. Atomic layer deposition is like chemical vapor deposition, except it's done in a stepwise process, where you expose your substrate to one material, for example, water. Let's say if we want to make zinc oxide, you'd expose your material to water, pump the excess water away so that you just have a self-saturating monolayer of water on the surface, and then you'd expose your substrate to a second material, like the metal source, maybe zinc, for zinc oxide. You make a self-saturating monolayer of the zinc, and then you pump away the excess, and then you just repeat that process over and over in a kind of digital way, and you can grow a film of oxides or sulfides or various other kinds of materials. So we built an ALD in a glove box so that we could do this without exposing our materials to air. And so in general, ALD is just one example of a matrix engineering type approach to try to change the various parameters with charge transport parameters within the film. So you can certainly use ALD to do things like improve the environmental robustness of the film, but also you can change delta alpha by eliminating surface states, and by choosing the right kind of material, you can, in principle, decrease the barrier height, so increase beta, while also decreasing delta alpha. All right, so I just want to end here. You conclude by saying that, I first described various kind of organic treatments that can be done with quantum dot films. And the mobilities right now for organic treatments vary between about 10 to the minus 4 to about 1 centimeters squared per volt second. Mobilities above 5 are available by using inorganic ligands, sulfide, thiocyanate, metal chalcogenide complexes, other kinds of approaches will also work, I think, pretty well. Existing quantum dot solids almost certainly have this situation, where the disorder is larger than the coupling, and that's going to mean that we have hopping transport as the governing charge transport mechanism, rather than mini-band transport. But however, this may be good enough. We don't necessarily need superlattices and mini-bands for a lot of applications. So for example, for solar cells, if we can increase the mobility from, say, 0.1 to about 50, which I think is possible using the techniques that we already have available to us, that results in about a 22-fold increase in the diffusion length, assuming that the lifetime doesn't change. And that increase in diffusion length would be sufficient to boost us over the 1 micron limit, which is kind of what we're shooting for. Okay, so although this is probably true for almost all quantum dot films, there are ways that we can flip this inequality. So the ways that we can think about to decrease delta alpha include coming up with novel syntheses that give much better size distributions than current syntheses do. That will decrease the delta alpha parameter. Finding ways to completely passivate surface states to remove the gap density of states. That will also improve the disorder, the energetic disorder. And especially with these very, very small ligands, we need to find ways to avoid heterogeneous necking and sintering. That's adding a lot of variability in the confinement energy of these particles. Right? So right now we kind of have probably random necking in various places. That causes some pockets to be very poorly quantum confined and other pockets of the film to be as quantum confined as they were in solution. And that leads to an increase in energy disorder, and that's going to reinforce that kind of relationship. So in addition to trying to decrease delta alpha, we can also try to increase beta, and I think one of the most promising ways to doing that is matrix engineering. So trying to find ways to put material between the quantum dots, very, very thin amounts of material, of course, that allow us to have lower barriers, that lower effective masses, and so forth. with that kind of strategy, it may be possible to enter the regime of actually block-like transport in these films. Okay, so I had a number of references kind of spattered throughout the talk, but I wanted to add a number of extras here at the end for those that are interested in reading further about this field of science. A couple of very good reviews here, and then some recent papers on some of the topics that I touched on today. So, thank you very much, and I'm happy to answer any questions.
So, questions? Yeah, go ahead.
Thank you. It was very informative talk. So my question is about that window layer. First, I would like to know what is the length of that field which is induced due to that window layer, and second, I would like to know why we don't use another window layer on the other side, because the other side there is still a metal contact and still a Schottky barrier.
Okay, so the idea on the back contact is to make sure that it's ohmic. And so some people have found good success just using normal metals, just metal deposition onto quantum dots and getting ohmic contacts. But also there are efforts where you put an interlayer in there to make sure that the contact is ohmic. So that is being done already. As far as the electric field distribution in the heterojunction region, I think that's something that a lot of people would be very interested in getting more information about. So I haven't seen any studies looking at the depletion width, for example, in the zinc oxide layer and the titanium layer. But it's probably going to be pretty small. Usually the doping in those materials is pretty high.
So this window layer, its role is only to induce this electric field, or it has other roles as well?
Well, so the first is to pass light to the active absorbing material, and then yes, to have the induced field in the depletion region right at the front of the absorbing material. So it's very much like it's a concept that's basically borrowed from thin film PV. Like cadmium telluride devices and SIGS devices use this concept. So it makes a lot of sense if you have a highly absorbing material with poor charge transport properties to have a window layer PN heterojunction kind of device design.
Thank you.
Okay. Yes, over here, Lee Garrett.
So you mentioned that you lose some of the quantum confinement effects. At least you lose that first exciton peak when you start annealing.
Yeah.
Can you speak a little bit to how that might affect MEG and things like that in these films? Do you get none anymore, or what? Have you looked at that? Or?
I don't think anybody's looked at that either yet. So people have looked at MEG in sort of normal organic coupled films, like hydrazine coupled films and EDT and so forth. And what's been found is that there's a huge amount of variability in the MEG yield depending on what the molecules are. Nobody's yet looked at the effect of, say, sintering, to my knowledge. If MEG really depends on having a strong quantum confinement effect, then you would expect it to be quenched or greatly reduced. But yeah, that's an open question, I think, as to when that will happen, or if.
Okay. Yeah, Gary.
So, the Schottky barrier is an N-type material. So, how on earth has it evolved through this material?
So you said the Schottky barrier is an N-type.
I think you said you treat hydrazine, like you said yesterday, that makes the quantum dot film N-type.
Yeah, for hydrazine, that's true.
Right, so you put the Schottky barrier, it used to be next to one of the metal electrodes, and now it's next to the oxide. Is that right? Did I see that diagram correctly?
No, so all of the other devices that I showed, all the solar cells are not using hydrazine. So in those materials, those films are P-type.
Okay.
So we're using EDT, for example, gives P-type film, and all of the NREL data is using. I wouldn't say that, but all the NREL data is using some form of ligand treatment that leaves a P-type film. Is that cleared up?
Really, I think I'll ask you again later.
Okay.
We'll talk about it.
Okay, other questions? Actually, I'd like to ask a question, if I may. So you talked about some transistor measurements of transfer characteristics to extract mobility. I'm wondering if in those measurements, do you see a dependence in the transfer characteristics on the ramp rate for the voltage? And if so, what rank rates do you end up
Yeah,
using?
sometimes yes. In most recent devices, no for our data. So we can do sweep rates as slow as say, 0.01 volts per second, all the way up to 50 volts per second, and we see basically the same behavior. There's a little bit of jitter in the data, but that's basically the same. Most other groups in the field would also say the same thing. They're doing quasi-static measurements typically, but I think if they ramped faster, they would also see very little difference. But in some types of treatments, we do see a large hysteresis. So for example, air-exposed films usually have an intense hysteresis effect, and that can be problematic as you go for extracting meaningful parameters.
Okay. Yes.
The recombination is bimolecular in this kind of device?
The recombination is bimolecular?
This kind of device, yes.
Yeah, I would say. And
And if yes, what about with increasing the mobility? The recombination also will be increased if it's bimolecular, because the absorption is more and you have more carriers. And how about the effect of the recombination of the coefficients?
yeah, so what we would like to do is to get in the process of studying much more the diffusion length rather than just the mobility. So if we can get a lot more information about lifetimes, then we can address those sorts of questions better than we're able to right now. So the field is basically focused on mobilities because, in some sense, they're a little bit easier, and also the field effect transistor is a nice platform to do these sorts of studies. People are also interested in using quantum dot films for transistors, large area transistors, and so that's quite natural. But there's been a lot less work done on measurements of diffusion links themselves. And that's, I think, where we need to go in order to address your question more fully.
Okay, anyone else? All right, if not, let's thank Matt once again. Okay, we'll take a break and reconvene at 9:30.